is a small video when I want to show the example where we're not working on the closed interval but are asked to find global maximum or minimum function. So for this example, for x positive, we are asked to find the x-coordinate of the absolute minimum for the given function, and there is no closed interval here. So we will be not using closed interval methods we learned for cases like that. But we will still be able to find an absolute minimum for the function. For you, I already plotted the graph for this function. This is a logarithmic function times x times 10x minus 11x. As you can see, indeed, it has some kind of minimum over here, and it seems like it is a global minimum, but we need to justify that and also find the location of this point. In this case, we only ask to find the x-coordinate. Well, let's start with the first step. We know what to do. When we are asked to find minimum or maximum, we know that probably we should start with differentiation. So let's find f prime of x. Looking at the function over here, I can see that we need to use product rule first for 10x times the natural log of x. U prime is 10, copy log, so it's 10 ln x, plus copy 10 over x, and then times derivative of the function of the ln x, which is 1 over x, minus 11x gives me 11. Let's simplify. The derivative becomes 10 ln x, then x can be simplified with x. 10 minus 11 is negative 1. And this is the derivative we got. Put it in the box because we will be using a sign line for the first derivative, and we will be plugging test points into this box. So what we're looking for? We're looking for critical points, as you remember, and critical points are coming from zeros and d and e points. Well, let's find where this function is 0. 10 ln x minus 1 equals 0. 10 ln x equals to 1. ln x equals 1 over 10. This is what we called logarithmic equation, or the equation that involves logarithmic functions. Usually the first step I always recommend to do is to isolate the log. So you see what I did? I isolated my log. The moment you isolated your log, you want to get rid of the log. To get rid of the log, apply exponential function to both sides. Then you will have e to the ln x equals e to the 1 over 10. But based on the properties of exponential and logarithmic functions, which is basically the properties or definition of the inverse functions, e undoes log, so e raised to the ln x is just x. X equals e to the 1/10. If this point is located on a domain, then this point is a critical point. Let's check the domain. The domain is over here. X should be positive because log does not exist for negative or 0 inputs, right? So since e to the 1 over 10 is positive, because e is something like 2.7, raised to the 1/10 it's still positive, and so on, then this is what we call critical points. For the d and e points, if you want to figure out where this derivative is d and e, we know that log does not exist for x less or equal to 0, but these points will not be critical points because they're not in the domain. So we have only one critical point, and we're gonna draw a sign line for the first derivative. And this is my notation. You don't have to follow this notation. I saw some students using a box method or any other method to organize their information, and you can choose any way you like it. I like to use a sign line where I'm going to put my critical point, and now I need to use, and I also want to identify the domain, so starting from 0 and not including 0. And I want to use test points. Test points are any points in those two intervals. Basically, our critical point divided the whole domain into two intervals, from 0 to e raised to the 1/10, and then from e to the 1/10 to the infinity. Test points can be any points, which we'll need to plug into the box. Remember I told you, keep the box over here. We're going to plug it here, and we just need to know this sign, plus or minus. Since we're expecting to have minimum, both from the graph and from the problem says find absolute minimum, and I see on the graph, indeed it is absolute minimum. We're expecting the first derivative to be negative and then positive, right? So let's check that this is the case. Not very convenient to use e to the 1/10 and then try to figure out test points if I don't know what approximately this number is. Well, it is approximately 1.105. Then for the test points, I can use, for example, e, because we're working with logs, and e is approximately 2.7, so that's good. And then for this one, I can use 1, right? Because 1 is less than e to the 1/10. So for the first interval, I will use test points 1. If I plug my 1 into over here into the box, and natural log of 1 is 0, 0 minus 1 is negative. So I'm going to put negative sign over here. If I plug e into the box, natural log of e is 1, 10 minus 1 is 9, which is positive. So I'm going to put plus over here, and I will use different color, and I will identify that the function is decreasing first, then it is increasing, and then this location over here, which is my critical point, e to the 1/10, is my minimum, but it's my local minimum. I cannot claim that this is the global minimum yet. And that's basically the whole complicated part of the problem. How should I claim that x equals e to the 1/10, which is my local minimum, by first derivative test? What should I say to claim that this is also global minimum? So here's a justification for you to understand. I would say that it is also x equals e to the 1/10 is abscissa, which is input x coordinate, of global minimum as well, because b/c means because there are no other critical points. There are no other critical points on the interval from 0 to e to the 1/10 and from e to the 1/10 to infinity. And since and we also should include that the function and f of x is decreasing on the left of x equals e to the 1/10, and then increasing, I would say even forever to the right, on the right, from x equals e to the 1/10. So the idea is, if there would be any change of the function behavior, for example, that was a minimum, and then the function was keep growing up, and then changed its mind, decided to go down, and now we have a lower minimum, and maybe now this is a global minimum, then you see this turn of the function over here, we would find it from the first derivative. The first derivative is exactly the best tool to locate all those changes of the behavior of the function. So this would be a critical point. We would find from calculations, but we did not find any, both on the right and on the left, and starting from 0. So from 0 to e and from e to plus infinity, we know the behavior of the function. It doesn't change. So we know it's keep decreasing and then it's keep increasing forever. That is why, even though the interval is not closed, we can, for this particular example, claim that this information is enough to say that e to the 1/10 is also a global minimum. And from the graph, you can see that actually it makes sense. Here it is. Here is on the graph. You see it's pretty close to 1 because I told you that x equals e to the 1/10 is approximately 1.1, so it makes sense, and this is exactly my global minimum, both local and global minimum. And that's a great example when we're working with some kind of functions. Even if you think about a parabola function concave up or parabola function concave down, even though we can work with these functions not on the closed interval but from -infinity to +infinity, we know that they have global minimum. That's for parabola. One more example. And global maximum, and these actually have even names called vertices. A vertex for parabola is either global maximum or global minimum, and we can justify with exactly the same idea. Since the function never makes any other turns, and we locate only one critical point, that critical point will be not only local extreme value, but also a global extreme value. Thank you for watching, and keep watching more videos about finding global or local extreme values to become really good at that.